All right, greetings, scholars. So, welcome. We are here at the top of week 6. So, I just realized an error I was doing with the discussions. I was updating the description, but I guess whatever post I was doing, it kept posting the same thing. So, it's okay if we move in a few weeks with kind of a repeated topic, which is okay. If you got submitted your discussions for those corresponding weeks on time, I gave you credit for it. It should be different topics going forward, right? So again, we're at the top of week 6 now. Our goal for this week, we want to get through chapter 3 on functions. So we're going to be it's 3 sections we need to get through this week. I totally got behind because just crunching or calculating grades for all of my students universally. So that kind of set me back, but it's okay. So we got grades submitted and updated. Let me say this about grades really quick. So, the grades are posted, and what they are, they're just a snapshot of where we are at this moment in time, right? So, I think we have grades through section 2.5. I did not include like week 4. So, I think I have weeks 1, 2, and 3 discussions along with the corresponding homework and quiz, the official quiz number 1, right? So, you should be able to see that on Populi. Check your grade. Check it for accuracy. If anything is out of order, contact me. Best way to contact me is a text message, or you can call that same number. And then also I do acknowledge that a lot of students, we're all adults, right? So people tend to choose to procrastinate. I'm guilty of it too, obviously. I usually like to have this stuff done in advance, but sometimes it just happens, right? So I just say that, to just try to discourage you all from procrastinating too much. So whenever possible, you want to try to get your assignment submitted promptly. Because if you try to wait until the end to submit this stuff, it piles up, and then a lot of times like internet servers become unreliable. You have a lot of students like nationwide and globally, honestly, trying to submit stuff at the same time, and it causes servers to like overload and crash and shut down and slow and be less effective, right? So idealistically, if you can get ahead, now obviously I'm creating these lectures as we go, so you can only get but so far ahead. But the homework is there, right? So you can try it in advance, and maybe you might be able to finish it. I want to say on all of our assignments, we get unlimited attempts. The system is set to take our highest score, and there should only be a 5% late penalty. That's with all assignments, homework, quizzes, and exams. I think we do have exam 1 coming up shortly. Okay, I think that's the meat and potatoes of what I like to say. So, again, I'm available if you guys have questions, comments, or concerns about anything. And let's move forward into chapter 3 on functions. So we're going to, here's a chapter outline. Let me see. So it looks like section 3.3 might be like a bonus lecture. I do want to go ahead and do a lecture for that section just to be complete, but I'm pretty sure you guys are not responsible for it. I think it replaces 3.3 or 4.1. So I'll be sure to get 4.1 in there and make it available for you all just in case questions pop up from that section. And more than likely, I'll probably just go ahead and do a presentation on section 3.3 as well. Okay. So today we're going to be working on section 3.1, functions and function notation. Okay. Oh, I like the slide. Man, like it. Learning objectives. In this section, you will determine whether a relation represents a function, find the value of a function, determine whether a function is one-to-one, use the vertical line test to identify functions, and graph the functions listed in the library of functions. Okay. So determining whether a relation represents a function. A relation is a set of ordered pairs. The set of the first component of each ordered pair is called the domain, and the set of the second component of each ordered pair is called the range. Considering the following set of ordered pairs, the first number in each pair are the first 5 natural numbers. The second number in each pair is twice that of the first. So the domain is going to be the set of natural numbers 1, 2, 3, 4, 5. The range is going to be 2, 4, 6, 8, 10. So note that each value in the domain is also known as the input value or independent variable and is often labeled with a lowercase letter x. Each value in the range is also known as an output value or dependent variable and is often labeled as a lowercase letter y. And this is a long section. It's 56 slides, so we still got 50 slides to go, but we're going to power through. So a relation is a function. Let me see. The way I remember, I distinguish like whether a relation is a function. Every y has to correspond to one x. You don't have one y or one output value that's associated with two different input values, right? No, I think I got it backwards. Let me think. Yeah, every y corresponds with one x. You don't have one y value that corresponds. Nope, I think I'm still saying it backwards. Yeah, I think I got it backwards, right? Every x corresponds to exactly one y. You don't have one x value that corresponds to two different y values. Yeah, that's better, right? So you don't have one input that goes to two different outputs, right? What I said initially was actually okay. That's another topic. So again, every x corresponds to exactly one y. You don't have one x that corresponds to more than one y, right? So for instance, this is what I like to call this a merge. Two different x's. Like if we were to plot this, like this would be something like if you had when x is -3, y is 2. When x is 4, y is also 2, right? So you have two different x values going to the same y, so they're side by side, right? So that one will be okay. I call this a merge. Now this comes up a little bit later with another topic. Again, every x corresponds to exactly one y. You don't have one x going to more than one y. But now in this third case, you do have one input value that corresponds to multiple outputs, right? So I'll call this a split. This is called a correspondence diagram, right? These three examples, these are called correspondence diagrams. And in the correspondence diagram, when we have the split, one input going to multiple outputs, you have one input that corresponds to multiple outputs. So then if we were to graph these outputs, these data points would be stacked on top of each other, right? And so that's when you have outputs that are stacked on top of each other, then it's not a function. Okay. Let me see. So a function is a relation in which each possible input leads to exactly one output. Again, every x corresponds to exactly one y. You don't have one x corresponding to multiple y's, right? We say that the output is a function of the input. The input value makes up the domain and the output makes up the range. Okay, I kind of want to get into an example. Let me see. So the coffee shop menu shown below consists of items and their prices. Is the price a function of the item? Let me see. Y is a function of x. So like for instance, normally I'm used to seeing it kind of like, I'll do this color. Normally we'll see it as like y as some function of x, something like this, all right? So it says, is the price, so if we were to rewrite it as like the price is a function of the item, some function of, I'm going to just call it the item. So what's our price? So like if we did x versus y, all right? So we had the plain donut, the jelly donut, and the chocolate donut. Then the outputs would be 1.49, 1.99, and 1.99, right? In order for this not to be a function, you would have to have one input corresponding to multiple outputs, right? And I don't think that happens. So is the price a function of the item? We can say yes. All right. The price, and this is our price over here, and this is our item over here, right? So this was part A. Okay, so is it a function of the item? Yes. All right. We don't have one input corresponding to multiple outputs. Then the part B asks us, is the item a function of the price? All right. So is the item a function of the price? So now the price is like our x value and the item is our y. So what, they just switched? So then if we switch these columns, 1.49, 1.99, and 1.99, and then this was the plain, the jelly, and the chocolate, right? Notice we have, when the price is 1.99, we have two different outputs. You could either have a jelly donut or a chocolate donut. I do not like stuff like this because it makes me hungry and I start thinking about this stuff. Then I want to go get it. Like a lot of times I'll be on YouTube and I'll see like little shorts on people making stuff or reaction videos to like, I guess it's mukbang or something like that. I don't know what that is, but it's like these people eating weird stuff, right? Or doing something ridiculous eating wise, right? But I try to limit myself to watching it because it makes me want to like, sometimes like like when they're doing recipes, it's like, man, I wanted to taste that. And then I find myself start snacking. So I usually don't like stuff, that tries to encourage me to eat. I'm like, yo, come on. But this one is not a function, right? We have one input that corresponds to multiple output. When our x is 1.99, it corresponds to either jelly or chocolate, right? So if we were to graph those output values would be stacked on top of each other. So that's an example of something that's not a function. All right. So and that was B. I'll put B here like this, right? So B, we got that it's not a function, but A, we got that it's, yes, a function. Okay. So I know it's a little bit jammed, but let's see, how do we do? So let's begin by considering the inputs as the items on the menu, the output values as the prices. So each item in the menu has only one price, so A is a function. We got that correct. So then for B, two items on the menu must have the same price if we consider the price to be the input. Therefore, the items are not a function of the price, right? We have one input that corresponds to multiple outputs, so then it's not a function. Okay, which is what we said. Okay. So determining if class grade rules are functions. In a particular math class, the overall percent grade corresponds to a grade point average. Is the grade point average a function of the percent grade? Okay, let me see. And then it looks like they might switch it. So I'm going to kind of build this one like I did the previous one, right? Again, I'm used to seeing it as y as some function of x, okay? So then it says, is the grade point average of a function of the percent grade? Grade point average, percent grade. So let's do G and P. So is the grade point average a function of the percent grade? Okay. Let me see. I'm running a little bit short on space. I'm gonna move this to the side. Oops. I'll just move it over here. Okay. So it looks like our inputs are the percent grade versus the grade point average, right? Okay. So the percents, we don't have any of these going to multiple outputs, right? They're all unique. They're not repeating. Yeah. So let me see. For the first question, wait a minute. Where is it? Is the grade point average, a function of the percent grades? We would say yes. So for the first question, we would say yes, a function. Okay. But then the second question says, is the percent grade, so I'll just kind of work it over here. Is the percent grade a function of the grade point average? So I think they switched it, right? So that now our inputs are the grade point average versus the percent grade. Now the grade point averages, do we have any repeats? If we have any repeating x's, it's not a function. 0, 1, 1.5, 2, 2.5, 3, 3.5, 4. Right? So because if these are our inputs and we don't have any repeating x's, then I think we're okay. So in either case, the x's did not repeat. So I think both of these should be yes, a function. So a telltale sign when working these, if you have repeating x's, then a lot of times it's not a function. I feel like both of these should be yes. Let's see, how do we do? For any percent grade, earned, there is an associated grade point average. So the grade point average is a function of the percent grade. In other words, if we input the percent grade, the output is a specific grade point average. In the grading system, there is a range of percent grades. Oh, we do have, I didn't even think about it proper, right? So for instance, when for the second part, I think we got the second part wrong. When the grade point average is 1, you could find multiple outputs for that. You can either have a 58% or a 60%, right? So for that input, you have multiple outputs, so then it's not a function, right? That should not be a function. Let me see if I see it here. It's not a function, right? So we got that one wrong. I just completely ignored that the percent grade was a range, right? So if we let the grade point average be our input and the output were our percent grades, we can choose an x and find multiple y's corresponding to x to make it not a function, right? So that one, we got that one wrong. I'm gonna just say it's not a function. Oops, let's go like this, like this. Yeah, and again, I got that wrong because I just ignored that this was a range, right? These were ranges, multiple values, right? So that's not a function, so we got that one wrong. Okay, I kept looking at it as like a unit. These are like funky the way they kind of accent this, but it's okay. Let's keep going. So we got to the bottom of that one. The notation y equals f of x defines a function named f. This is read as y is a function of x. The letter x represents the input value or independent variable. The letter y or f of x represents the output value or dependent variable. I feel like that's not too terribly bad. Use function notation to represent a function whose input is the name of a month and output. So, okay. So f of, let me see, the name of a month. Use function represent a function is the name of a month. So I just label it as month for right now. And whose output is the number of days. And then days in the month. Assume that the domain does not include leap years. I don't know that we necessarily need to actually find that actual function. I think we just need to describe it in some manner like this. Let's see how this is expressed. So f of that month equals the output, right? The number of days in the month is a function of the name of the month. So if we write a function f, we write the days equals f of the month. That's fine. I think what we have is fine. So for instance, f of March equals 31 because March has 31 days in it, right? Yeah, so that's okay. I think what we have is fine. Note that the inputs to a function do not have to be numbers. Functions of inputs can be names of people, labels of geometric objects, or any other element that describes some kind of output. However, most of the functions we'll work in this book will have numbers as inputs and outputs, okay? So a function n equal to f of y gives the number of police officers in a town in a year y. What does f of 2005 equal 300 represent? All right, so if y, a function in the year, so y represents the year. So this is basically saying, so if we have f of 2005 equals 300, that means that what, in the year 2005, this town had 300 officers. Okay, that's essentially what it means. So in the year 2005, this town had 300 officers. So when we read f of 2005 equals 300, we see that the input year is 2005. The value for the output, the number of officers, is 300. So this statement tells us that in the year 2005, there were 300 officers in the town. Okay. Let me see a question here. So instead of a notation such as y equals f of x, could we use the same symbol for the output as the function such as y equals y of x, meaning y is a function of x? I think this goes like, yeah, we can do this, but we try to make a distinction between input and output. If we labeled it like this, it's easy to confuse. Okay, like, are we talking about the input or the output? And so you'd have to dig a little more to get the context. So we usually use different labels to represent the input and output. Let's see, something like that. Yes, this is often done, especially in applied subjects that use higher math, such as physics and engineering. However, in exploring math itself, we like to maintain a distinction between a function such as f, which is a rule or procedure, and the output y. We get by applying f to a particular input x. This is why we usually use notations such as y equals f of x or p equals w of d and so on, right? So just to minimize confusion, we do try to use distinct labels. Okay, battery looks okay. Let's keep going. All right, so I know this one might be a little bit small, so we'll do the best that we can. It says, which table represents a function? So in this context, this is what we have our set of inputs versus our outputs. You can consider this a correspondence diagram, but basically, if we have repeating x's, it's not a function, right? If it's dysfunctional, just kind of like in life, right? If we are constantly going back to our x, there might be a little bit of dysfunction there. It's similar to this, right? So if we have repeating x's, it's not a function. I think that's safe to say, right? So no repeating x's. If we were to plot all these, none of these would be stacked on top of each other. So we would say the first one is a function. So we'll say that yes, a function. Okay. Do we have any repeating x's? No repeating x's. I would say that this is a function. And then notice here we do have repeating x's. All right. If we were to plot these ordered pairs, when x is 5, y is 2. When x is 5, y is 4. So those two ordered pairs will be stacked on top of each other. When you have ordered pairs stacked on top of each other like that, then it's not a function. So this one should not be a function. And another way you can identify that is because we have repeating x's. Okay, I feel good about this one. So table 6 and 7 define functions, and both each input value corresponds to exactly one output, but table 8 does not define a function because the input value of 5 corresponds to 2 different output values. Okay, we're gonna go forward. So evaluate this function when x is 2a and a plus h, and then they want us to find f of a plus h minus f of a over h. Okay, that's fine. Let me say I work part A here. So when x is 2, they're asking us to find f of 2. So basically, we replace each x with 2 and evaluate it. So we have x squared plus 3x minus 4. I replace each x with a blank set of parentheses, and then I plug in my value that I'd like to evaluate into the parentheses. 2, 2, 2. Okay. So that's going to be what? 4 plus 6 minus 4 looks like it's ultimately 6 for part A. I'll start part B up here. So then we're asked to find f of A. F of A. I'm replacing each x with A. First, thing is making noises so distracting. Oh, give me just a moment. Come on. I turned you off so that you wouldn't be a distraction. Come on. So I'm trying to get it to stop making this clicking thing noise, and it started making more clicking noise. And I have it turned off. Come on. Here, let's just turn this off. Come on, stop. Thank you. Hopefully it's done. All right, we're not gonna worry about it. All right, I just needed to stop while I'm recording, then it can make all the noise at once later. Oof. Okay. All right. So nothing cancels, nothing simplifies, so we can just kind of leave that as is. A squared plus 3a minus 4. Okay, that's the result for part B. C asks us to find f of a plus h. A squared plus 3a. Kind of run a little bit short on space. Again, we're replacing x with a plus h. A plus h and a plus h. Okay, we should probably expand this. So then a plus h squared is going to become, let me see, a squared plus 2ah plus h squared plus 3a plus 3h minus 4. I don't think anything cancels, so that's our final result there. And then for D, they want us to evaluate f of a plus h. We did that already, minus f of a, all divided by h. So this is actually what's called the difference quotient. So we're taking our result from C minus our result from B, simplifying it, and then dividing that result by h. So I'm going to put an equal signs here. It's going to go like this. Okay. So from C, we have all of this, a squared plus 2ah plus h squared, 3a, 3h minus 4. And then we want to say minus the result from B. Since we're subtracting B, we really need to distribute a negative into that. So I'm going to distribute my negative. So minus a squared minus 3a plus 4. Okay. Let me go ahead and finish this part out. So I think we have some items that cancel. A squared cancels a squared. 3a cancels 3a. The 4 cancels the 4. So then what's remaining, and again, we're going to do all of this over h. So then what's remaining, we have this. Now, just because I'm running short on time, notice that the terms that are remaining all have h in them, which is what we kind of anticipated. So I'm going to go and factor out a h from each of those as well. So if I factor out h, we're going to have 2a plus h plus 3 divided by h. Now we get our h's to cancel. And the final result we get is 2a plus h plus 3. Okay. Okay. So that was an adventure. Let's see. So that's called a difference quotient. That's leading into this major topic in calculus. It uses this. You know, we have actually we have like shortcuts where we can bypass all of this, but this leads into a major topic in calculus. Okay, my battery, let me go ahead and put it in a low power mode. Okay. So we got 6, we got all of that. Let's kind of look at our prepared notes. I see the 6, you can see it here. I think we got this result, we got that one. Ultimately, I think we got this, right? So this is a type version. You might need to like screenshot this and to blow it up or whatever. Okay, let's keep going. So given this function, evaluate h of 4, okay? So again, we're given h of p equals p squared plus 2p. We're asked to evaluate this function when p is 4. So that's going to be p squared plus 2p. Notice I replaced the p with a blank set first, and then I plug in a value of 4 into the parentheses. And we do that because like it helps us to keep track of signs, like when we're working with negatives. Okay, we're less likely to make mistake when we do it that way. So then 4 squared gives us 16. 4 times 2 is 8. So what is that, 24? So we got a result of 24 there. And 24 is good. Okay, we're about halfway. Let's keep going. All right. Okay, so we're given that h of p equals p squared plus 2p. And we're asked to, if we set h of p equal to 3, they want us to work backwards and solve for p. Okay. So this is kind of like setting your y equal to 3 and solve, right? So then we have our p squared plus 2p equals 3. I'm going to set it to 0, so subtract 3 on both sides. So then we have p squared. Let's see, we got this minus 3, 2p, and p squared equals 0, right? We just subtracted 3 on both sides. Okay, so then something like this, we should be able to factor. Okay, p and p. Because my second sign is negative, I know my two signs are going to be opposite. So One's going to be positive and one's going to be negative. The first sign tells me the sign of the larger number. We're looking for two numbers that multiply to give us -3 and add to give us +2. And I think that's 3 and -1. Okay. Notice that 3 times -1 is -3. 3 plus -1 is +2. Okay. So then now we can apply the zero factor property. We have two or more things that multiply to give us 0. So we set each factor to 0 and solve. And ultimately we get P equals -3 and 1. Okay, we should check it in the context of the original. I'm just going to be a little bit lazy here and use my prepared notes. So -3 and 1. Is that all the x's? So when x is -3 and x is 1, the corresponding y is 3. Okay. Okay. Let me see. Express this as a function p equals f of n if possible. So we're given 2n plus 6p equal to 12. Okay. And they want us to write p as a function of n. So basically solve for p. So first we can subtract 2n on both sides of the equal sign. Those are unlike terms, so we just leave them separate on the right hand side. The equal sign comes down. Again, on the right hand side, those are unlike terms. So 12 minus 2n, and the 6p comes down. If we're trying to solve for p, divide both sides by 6. So then p equals 12 divided by 6 is what, 2? 2 divided by 6 is a third. So now we wrote p in terms of n. So we wrote p as a function of n. 2 minus 1/3 n. Okay, that's correct. It's important to note that not every relationship expressed by an equation can also be expressed as a function with a formula. So does this equation represent a function with x as inputs and y as the output? So can we express this equation as y as a function of x? If we try to solve for y, all right, let's try to solve for y and see what happens. So we have this, F around and find out. So we have this x squared. We have x squared plus y squared equals 1, right? Let's solve for y. So then if we subtract x squared on both sides, we get what? 1 minus x squared, right? Then when we take the square root, take a moment. What symbol do we have to include whenever we take the square root? All right. So if we take the square root on both sides, we have to include plus or minus. Because of that plus or minus, we can have one x value. It's going to force it to be where we have one x value corresponding to more than one y value. So then that means this is not a function. So does this equation represent a function where x is an input? Can we express this as a function, y as some function of x? The result here would be no. No, not a function. Because you could find one x value that corresponds to multiple y values because of that plus or minus. Okay. So subtracting, yada, yada, yada. We get two outputs corresponding to the same input. So this relationship cannot be represented as a single function, y equals f of x. Are there relationships expressed by an equation that do represent a function, but which still cannot be represented by an algebraic formula? Are there relationships expressed as an equation that do represent a function, but still cannot be represented by an algebraic formula? I'm going to say yeah. Let's just look and see. Let me see. This can happen, for example, given this equation, x equals y plus 2 to the power of y. If we want to express y as a function of x, there's no simple algebraic formula involving only x that equals y. However, each x does determine a unique value for y, and there are mathematical procedures by which y can be found to any desired accuracy. In this case, we say that the equation given gives an implicit or implied rule for y as a function of x, even though the formula cannot be written explicitly. All right. So even though we can't write this explicitly as y as a function of x, it is a function. Let me see. Yeah, it's interesting. I'm going to kind of let that be. Let's go. Oh, let's see what the low power does. It causes my screen to dim a lot sooner than I would like. We're actually making pretty good time. I mean, it's taking time, but we're almost there, actually. We're not too far from the end of this section. All right, so using table 11, evaluate g of 3 and then solve g of n equal to 6. Okay, so for part A, it asks us to evaluate g of 3. So that's saying when x is 3, what's the corresponding y, right? Or when n is 3, the corresponding y is 7. So g of 3 should be 7. So for part A, g of 3 equals 7. And I pretty much just took that straight from the chart, from this table 11. And then for part B, they're saying when your y value is 6, what's the corresponding x? Or in other words, if we have g of n equals 6, which is here, corresponding x is 2. In other words, we say n equals 2. Again, just taking it straight from the chart. Okay, I know. All right, and I could plug in my tablet. I'm using the port for my microphone, but I have an adapter so I can charge and use the microphone. But I'm just trying to finish this out before the battery dies. So we're going forward rolling. Okay, for A, I think we got 7. Oh, wait a minute. Were there multiple solutions? No, I didn't see that. 6 and 6. Oh, shoot. Moving too fast, right? N is 2. I didn't even see that other one. Let me highlight it. So when N is 6, we got this one, but we also have this one. Is that okay? As long as you don't have repeating x's. We don't have repeating x's. So then N is 2. So we also needed to say that N was 4. Okay, so two different value of x give you the same y. So these results, if we were to plot them, they would be side by side, and that's okay to happen. It'll still be a function, even if those are side by side. So I definitely missed the second one. Reduces an output of 6 if it shows 2 solutions, right? So when we input 2 into the function, output is 6. When we input 4 into the function, so it's 6. Yeah, we had 2 inputs that generate that output, and that's okay. Again, for function, and we're going to have, I'm holding off on giving another explanation for this. I'm trying to wait until it shows up in the notes. Let's just put a pin in it because I know it's coming up. Let's just kind of keep going. Okay, so given the graph in figure 4, evaluate f of 2 and solve for f of x equals 4. Okay, so for part A, when x is 2, what's the corresponding y? So when x is 2, right here, corresponding y is 1. So then for part A, we can say that f of 2, when x is 2, the corresponding y is 1. Okay. So then for part B, they ask us to solve f of x equal to 4. So when our y value is 4, I'll highlight it like this. Style, I want a dash line right like that. Okay. So when our y value is 4, what's the corresponding x? Let me copy, paste. So here, we see one of them here. Copy and paste. The other one's here, right? So the corresponding x, it looks like we have 2 of them. When x is -1 or when x is 3, those both generate an output of 4. Because 2 different x values generate the same y, and that's okay. Okay. So when x is 2, the corresponding y is 1. And then we have two different x values that'll produce the y value of 4. So a one-to-one function is a function in which each output corresponds to exactly one input, right? So for one-to-one, that means every y, I think for a function, what we said originally, every x corresponds to exactly one y, right? You don't have one x corresponding to multiple y's. Now for a one-to-one function, we're saying every y corresponds to exactly one x, okay? So for a function, every x corresponds to exactly one y. For one-to-one, every y corresponds to exactly one x. So is the area of a circle a function of its radius? If yes, okay, so what? Generally for area of a circle is what? Pi r squared. Okay, so if we were to graph this, the radius versus the area, this would just be a parabola, a U-shaped curve, right? So, you know, we can choose several values of x, like let x be -3, -2, -1, 0, 1, 2, 3, and find the corresponding y's, plot the points. We'll get a U-shaped curve, all right? So notice we have no repeating x's. So then, is this a function? We would say yes, all right? Yes, a function. Okay. But then is this a one-to-one function? In order to be a one-to-one function, we cannot have repeating y's. I think if we have a U-shaped curve, it's similar to this image here. We're going to have repeating y's, multiple x values that have the same y output, right? So then is it one-to-one? And we're going to say it's not one-to-one. Okay, it is a function, but it's not one-to-one. Okay, I'm still holding off on a more simple explanation. Okay, I'm going to let that be for now. Okay, so this is what I was holding off for, right? So in a graphical sense, we have the vertical line test that tells us whether it's a function. The vertical line test says that, like, as long as we can draw a vertical line, and no matter where we place it on our relation, as long as it touches the graph once, then it's a function. But if we can draw a vertical line and it touches the graph more than once, then it's not a function. Right? If we can draw a vertical line and it touches the graph more than once, then it's not a function. All right? So this is why I kept alluding to originally, if the points are stacked on top of each other, it's not a function. Right? If we have repeating x's, then it's not a function. So I was really using the vertical line test. I was just not saying the vertical line test because I was trying to hold off until it appeared in the notes, right? But so for me, you know, if I were to visualize plotting these ordered pairs, and if they're stacked on top of each other, then it's not a function because it fails the vertical line test, right? Okay. So that's for functions. So which of these graphs represents a function? So A is a function, B is a function, but it should be clear that C is not a function because we can draw a vertical line and it'll touch the graph more than once. So A and B are functions and C is not. And you can see here, we can draw a vertical line and it touches the graph more than once. So C is not a function. Okay. So the vertical line test tells us whether or not a graph is a function. This is the other piece that I was holding out on. The horizontal line test tells us whether or not a graph is one-to-one, right? So one-to-one means that every y corresponds to exactly one x, right? Consider the functions in 9a and b. Are either of the functions one-to-one? Did we skip? Why does it feel like we skipped? Oh, and figure 9a and b, right? So here, so are either of these one-to-one? So we use the horizontal line test. If we can draw a horizontal line and it touches the graph more than once, then it's not one-to-one, right? So notice in B, no matter where we draw a horizontal line, it only touches the graph once, right? But in A, we can draw a horizontal line and it touches the graph more than once. So then we would say that A is not one-to-one and B is one-to-one. Right? And we have it here. So A is not 1-to-1. We can draw a horizontal line and it'll touch the graph more than once. B is 1-to-1. Any horizontal line is going to intersect the diagonal line at most once. Okay, we're almost there. 10 slides. Okay, so then this final part. So I'm going to do a quick recap, at least on like functions. I think what the conclusion we came to. So given a relation or a correspondence diagram or any kind of, image like that or whatever, every x needs to correspond to exactly one y. In other words, so that's like the image passes the vertical line test. If we can draw a vertical line and it touches it more than once, then it's not a function. So like when we had those correspondence diagrams or those tables, if we were to plot those points and those points are stacked on top of each other, then that's an example of something that's not a function. Now you can have something that is a function, but it might not be 1-to-1. 1-to-1 means that every y corresponds to exactly one x. A good example to show something that is a function but it's not 1-to-1 is a parabola, a U-shaped curve, right? So the parabola is a function. It passes the vertical line test, but it fails the horizontal line test. The vertical line test tells us that it is a function. The horizontal line test tells us that it's not a 1-to-1 function. Okay. All right. So here with functions, with this last set of information, we're kind of like, you'll hear me refer to this as a library of basic functions. Sometimes you'll also hear me refer to it as a library or collection of parent functions. Sometimes I refer to these as basic functions. Sometimes I refer to them as parent functions. And so what we're doing is we just have a collection of base functions that we're going to be using going forward to we're building a case for like graphing, right? And so we have a good amount of basic or parent functions here that we're going to use going forward, right? So the first parent function that we have is called a constant function. And that's like when you have y equals some number or f of x equals a c. If you just have y equals some number, that means it's just a flat horizontal line through whatever that number is, okay? So no matter what x value you choose, y is always the same, a flat horizontal line. That's called the constant function. The next one we have is the next base function is called the identity function. That's like y equals x, right? So whatever x you choose, y is going to be the same, and that graph is just going to be a diagonal line, right? A diagonal line through the origin. Now, going forward, again, this is like the foundation for graphing that we have, and then in subsequent sections, we're going to look at how we can manipulate these base functions to generate graphs, right? We're going to be doing manipulations on these base functions. Okay, so that was the identity function. Next, we have the absolute value function. That's y equals the absolute value of x. And absolute value is basically the positive distance away from zero number is. So for instance, when we calculate the absolute value of -2, it spits out +2. All right. Absolute value of 0 is 0. And this is the general shape for absolute value. Okay. Next, we have a quadratic function. So that's like y equals x squared. This one we've kind of explored today. Whatever our x value is, we square it, and it generates a y value, and the image looks like this. So this is the general shape for a quadratic function. It's like a U-shaped curve or a parabola. Then we have a cubic function. It's almost like an S, like a vertical S or something. This is the general shape for a cubic function. Then next, we have the reciprocal function. So reciprocal function is y equals 1 over x, and this is the general shape for a reciprocal function. And we're going to be doing manipulations on these. Notice that the reciprocal function has a horizontal asymptote, which is the x-axis. We get really, really close to the x-axis, but we actually never reach it. And then this also has a vertical asymptote as the y-axis. Again, we get really, really close to the y-axis, but we never reach it. All right. Okay. So this is the reciprocal function. So next we have a reciprocal squared function. Reciprocal squared, right? It looks like this. So it's like the negative values, the negative x values became positive. All right, so they just flipped. and the positive y's kind of stay the same. Okay, but this is the general shape of the reciprocal square function. And then next we have the square root function. The way I remember the square root function is I remember it as the general shape for a square root is the top half of a sideways parabola. So if we take a U-shaped curve and turn it to the right by 90 degrees, cut it in half and remove the bottom, then the square root function is the top half of a sideways parabola. That's how I remember square root function, the general shape of it. And lastly, we have the cube root function. All right, cube root is like square root, but then we have that extra part going off to the left. Okay. All right, and with that, that brings us to the end of what we would like to talk about, with 8% health left on the clock. So I'm still have to make the PowerPoints for section 3.2. I'll do the best that I can. You know, it should be out shortly. We'll do a presentation for section 3.2. I'll go ahead and do a presentation for 4.1, and then there'll probably be a bonus lecture for section 3.3. I don't think you're necessarily directly responsible for it, but I want to go ahead and do a presentation on it anyway, just to be complete. Okay. All right. And with that, we're going to go ahead and end the session here. And from one beautiful mind to another, have a great day. Take care. Peace.